What if I told you there's a catastrophe headed straight for Earth, and it's been in motion for over 2 million years? Not a comet, not a rogue asteroid, something far bigger, a galaxy. Right now, at this very moment, the Andromeda Galaxy is closing in on us at more than 186 miles per second. But before we get to that collision, and we will get there, I want to start with a mystery that puzzled astronomers for decades. A single night in 1885 that nobody could explain. Picture this, September 1885. Observatories from Europe to North America are buzzing. A brilliant new point of light has erupted near the Andromeda Nebula, what astronomers of the time considered an unremarkable smudge on the edge of our own galaxy. For a few weeks, this newcomer outshines everything around it. It gets a name, S Andromedae. And then, 6 months later, it simply disappears. Gone. No trace. The calculations didn't add up, the brightness made no sense, and for years nobody could agree on what they'd actually seen. I've spent decades studying this period of astronomical history, and I'll tell you, the answer, when it finally came, was more stunning than anyone had dared to guess. Here's the thing, though, in 1885, nobody really understood what they were looking at. The tools for measuring cosmic distances simply didn't exist yet. The glowing smudge in the constellation Andromeda, also known as M31, was thought to be just a reflective nebula sitting somewhere on the outskirts of our own Milky Way. I've spent decades studying this period of astronomical history, and it's remarkable how profoundly wrong that assumption turned out to be. By the 1920s, observations by Edwin Hubble and others had settled the question. The Andromeda Nebula wasn't a nebula at all. It was a full-fledged galaxy, comparable to our own, sitting at an almost unimaginable distance. In the century that's followed, our picture of Andromeda has sharpened considerably. What we now know is that M31 is a spiral galaxy containing approximately 1 trillion stars. Its diameter stretches more than 150,000 light-years. That's roughly 900,000 trillion miles across. Its total mass falls somewhere between 800 billion and 1.5 trillion solar masses, which puts it in roughly the same weight class as the Milky Way. You know what's interesting? That relative lightness actually tells us something. Andromeda is packed with dim red dwarf stars and appears to contain somewhat less dark matter than you might expect. Take that combination, and you get a galaxy that punches above its visual weight. Like every spiral galaxy worth its salt, Andromeda has a dense central nucleus, millions of tightly packed stars crowded into a region so blazingly bright that it overwhelms observational instruments. You literally cannot pick out individual stars through that glare. That's exactly why it took so long to track down the remnant of S Andromedae. Historical records clearly placed the explosion near the galactic center, but finding the actual debris was another matter entirely. It wasn't until 1988, 103 years after that brilliant flash in 1885, that astronomers finally identified a small dark nebula sitting just off the nucleus, standing out as a shadow against the dazzling central glow. Spectral analysis confirmed it. That shadowy smudge was all that remained of Essie Andromedae, making it the first supernova remnant ever identified beyond the Milky Way. Now, spend a little time examining Andromeda's center, and something unusual jumps out at you. This galaxy has a double nucleus, a feature that sets it apart from virtually every other spiral system we've studied. The brighter, more expansive component sits slightly off the geometrical center of the galaxy. It's a sprawling supercluster of luminous stars, spanning about 7 light-years. The dimmer, more compact component, roughly 1.3 light-years across, sits closer to the true center. Current models suggest it harbors a supermassive black hole approximately 50 million times the mass of our Sun. What caused this peculiar arrangement is still being debated. One school of thought holds that Andromeda consumed a sizable satellite galaxy long ago, and that bright concentration is the leftover core of that unfortunate neighbor. A competing hypothesis argues for a single, unified nucleus, whose apparent duality is nothing more than an optical illusion, the product of an opaque dust lane splitting the view. Given how far away Andromeda is and how awkwardly it's angled, toward us, gathering conclusive evidence for either explanation remains, for now, out of reach. Moving through Andromeda's central region, you encounter one of its strangest residents, an object whose full designation is a bit of a mouthful, but whose behavior is nothing short of remarkable. Optically, it's essentially invisible. Even the most powerful conventional telescope will show you nothing. But switch to X-ray observations and suddenly this object blazes as the brightest single point in the entire galaxy. What astronomers have pieced together is that it's a binary system. One partner is a neutron star, a city-sized object only a few dozen miles across, spinning once every 3 seconds. The other is almost certainly a red giant, significantly larger but far less energetic. Combined, the two weigh in at no more than 3 solar masses. Every 4 hours, the neutron star passes behind its companion, causing a sharp drop in X-ray output before the signal rebounds to full strength. The proximity of the two objects strongly suggests that the neutron star is actively drawing material away from its partner, slowly cannibalizing it. Calculations put the duration of this process at several tens of millions of years. When it's over, tidal forces will shred the red giant into a brilliant ring-shaped nebula. That extraordinary object is just one member of a vast stellar crowd surrounding Andromeda's nucleus. Taken together, these stars form a bulge about 12,000 light-years in diameter, noticeably elongated in shape. Andromeda also has a bar structure, though it's oriented edge-on from our vantage point, making it nearly invisible from Earth. Estimates put its length at around 17,000 light-years, and its width at roughly 6,500 light-years. All told, the central region accounts for about 30% of the galaxy's total mass. Step back far enough, and the real grandeur of Andromeda reveals itself. 2 enormous spiral arms sweep outward from the ends of that central bar in sweeping, majestic curves. Between them lie dark gaps that are strikingly wider than their counterparts in the Milky Way, up to 13,000 light-years across in places. Those arms hold roughly 56% of the galaxy's stellar mass, along with a healthy dose of dark matter. Gravity compresses interstellar gas and dust within the arms, generating active star-forming regions. Over time, those molecular clouds collapse into open clusters and stellar associations filled with young, brilliant stars. Their combined light, scattered and reflected off surrounding nebulae, gives the galactic disk that breathtaking multicolored shimmer you see in deep-field images. I've spent decades studying massive stars, and few objects fascinate me more than AE Andromedae. Nestled inside one of those star-forming associations, it ranks among the most luminous stars in the entire galaxy. It's a hot blue giant, what astronomers call a luminous blue variable, and its brightness fluctuates with no predictable pattern whatsoever. There are only a few dozen known objects of this type in the observable universe. The extreme temperatures and pressures in AE Andromeda's outer layers keep the whole star in a state of perpetual near instability. Internally, currents of plasma collide in chaotic, essentially unpredictable ways, triggering eruptions that can multiply the star's luminosity by tens of times in a short period. Theoretically, the most violent such event could amplify its brightness by millions. An event astronomers call a pseudo-supernova. It could happen tomorrow. It could happen in 1,000,000 years. Nobody knows. Pinning down the physical parameters of such an unstable star at a distance of 2.5 million light-years is genuinely difficult, but modern high-precision instruments have given us a reasonable picture. AE Andromeda's mass sits somewhere between 50 and 120 solar masses. At the peak of its pulsations, its radius swells to about 55 times that of our Sun, just slightly smaller than Mercury's orbital path. Its surface temperature hovers near 20,000 Kelvin, and its luminosity exceeds the Sun's by somewhere between 500,000 and 700,000 times. Like all blue giants, it drives a ferocious stellar wind, outflowing material clocked at speeds approaching 62 miles per second. At that rate, the star loses roughly 2 quadrillion tons of mass every second. Every year it sheds material equivalent to 10 Earth masses. For a star this size, though, that loss is almost negligible. It will exhaust its nuclear fuel long before wind erosion makes any meaningful dent in its total mass. At only 2 million years old, A.E. Andromeda is already old by the standards of massive stars. Estimates suggest it will detonate as a supernova within the next million years, leaving behind a black hole wrapped in an expanding gas and dust nebula. You know what's interesting? Stars in Andromeda aren't distributed uniformly, and that uneven distribution is actually a window into the galaxy's history. The oldest stellar populations, dating back 11 to 13 billion years, are concentrated in the nucleus. The disk and spiral arms, by contrast, are dominated by comparatively younger stars, formed roughly 3 to 4 billion years ago. Embedded in those arms are star-forming nurseries, producing some of the youngest stars in the galaxy, some only a few million years old. The implication is clear. In its early days, M31 was considerably smaller and rounder, closer to elliptical than spiral in shape. Now, here's a concept I find both intriguing and usefully humbling: the galactic habitable zone. The crowded, radiation-drenched central region of Andromeda is hostile territory for life. Orbital dynamics near the core are chaotic, and the radiation environment would be merciless to any biology we can imagine. Meanwhile, the outer fringes of the galaxy are chemically impoverished, too deficient in heavy elements to form rocky, Earth-like planets in any abundance. That leaves an intermediate ring, a Goldilocks band at intermediate distances from the center, as the plausible zone where complex life might conceivably arise. Within that zone, at a distance of tens of thousands of light-years from the nucleus, sits a dim, unassuming star designated Mega ML7. Mega ML7 is a red giant with about half the mass of our Sun. In 1999, astronomers got lucky. A microlensing event, essentially the galaxy using the star's gravity as a natural magnifying glass, allowed a much more detailed study of this otherwise unremarkable object than distance alone would normally permit. Mass, spectrum, surface temperature, all were measured. The surface temperature came out at roughly 3,700 Kelvin, but the most exciting result was a rhythmic deviation in the star's path, a subtle wobble that, by the accepted logic of planetary detection, suggests the presence of a massive companion. That candidate object, designated Mega ML7b, is considered a potential exoplanet, and if confirmed, it would become the first exoplanet ever identified outside the Milky Way. Current estimates suggest it's likely a gas giant with roughly 6.3 times the mass of Jupiter. What makes the system genuinely exciting is that its chemical composition appears diverse enough to accommodate a full range of planetary types, not just gas giants, but potentially rocky terrestrial bodies as well. Let me share something fascinating about Andromeda's stellar neighborhoods. Compared to the Milky Way, M31 is extraordinarily rich in star clusters and associations. The catalog currently includes around 460 globular clusters, roughly 10,000 open clusters, and several dozen large stellar associations. Some are concentrated near the center, others are scattered through the disk, still others are embedded in the spiral arms. Among the most visually striking is NGC 206, sitting near the very edge of the galactic disk. NGC 206 was once classified as a globular cluster, but its sheer scale eventually earned it a promotion to stellar association. Within a radius of about 200 light-years, it packs approximately 300 exceptionally luminous stars, plus countless dimmer ones, adding up to a combined mass of roughly 200,000 solar masses. Its collective brightness is so overwhelming that it's visible from Earth through an amateur telescope, standing out alongside the nucleus and spiral arms. The association apparently formed from the merger of at least two large molecular clouds, separated by a lane of interstellar dust, one roughly 10 million years old, the other around 50 million. Their gravitational fusion created a massive accumulation point for surrounding gas, which in turn triggered a region of prolific star formation on a grand scale. In time, some of those stars will disperse into the broader galaxy, while the remainder will coalesce into a dense globular cluster. I've spent decades studying galactic collisions, and Andromeda's history is a catalogue of them. Over its lifetime, M31 is believed to have consumed more than 100 satellite galaxies. Some were absorbed without leaving a trace. Others were shredded into vast stellar streams, rivers of stars stretching across tens of thousands of light-years. The most dramatic collision on record involved an object now known as M32. This compact elliptical galaxy hangs above Andromeda's disk, just 17,000 light-years away. It's small, about 8,000 light-years across, yet it carries a mass of roughly 1 billion solar masses and contains a supermassive black hole about 2.5 million times heavier than our Sun. Impressive statistics for such a diminutive object. But M32 is not what it once was. Data from the Spitzer Space Telescope tells a story of violence. Around 800 million years ago, a much larger galaxy, the predecessor of M32, punched clean through Andromeda's disk at high velocity, blasting a hole in one of its spiral arms. In that collision, M32 shed the overwhelming majority of its stars. Reconstructing its original form is essentially impossible at this point. It may have been a full elliptical galaxy or a small spiral, and only its dense central remnant survives. Beyond M32, Andromeda maintains gravitational dominion over roughly 30 satellite galaxies. The most conspicuous is M110, spanning about 15,000 light-years. Most of the remaining satellites are dwarf spheroidal galaxies distributed within about 1 million light-years of the main disk. Together they constitute the Andromeda subgroup, a component of the local group. The local group also includes the Milky Way and its own retinue of satellites, the Triangulum Galaxy, and a scattering of smaller objects. Gravity is pulling all of them toward a common center, slowly but with absolute inevitability. Andromeda is currently closing the gap between us at more than 186 miles per second. Within a few billion years, the two galaxies will merge, forming a massive elliptical system. The gravitational forces involved will scatter the stars of both galaxies across space in entirely unpredictable patterns, a process astronomers call Milkomeda, or sometimes Milkdromda. By that point, Earth's story will almost certainly be over. Our Sun will be in its dying phase, having scorched the planet's surface beyond any possibility of habitability, or Earth itself may have been swallowed entirely as the Sun expands into a red giant. What becomes of humanity by then is a question no equation can answer. Will our descendants have spread across dozens of star systems, transformed beyond recognition by millions of years of evolution and technological change? Or will our species have vanished entirely, like the countless life forms that arose and disappeared in the billions of years before us? I've spent my career looking up at the sky and asking big questions. That one, I'll admit, is the biggest of all, and I'm comfortable with not knowing the answer.